I'd like to talk briefly about the techniques that Zach Slepian, Jianmin Hao, and I have used in our studies of the 4-point galaxy correlations. I'm going to begin with an analogy to atomic physics, which I think will be helpful. Let's consider a lithium atom with 3 electrons. The ground state, of course, has 2 electrons in the 1s and 1 electron in the 2s. We can imagine excited states of lithium where the 3 electrons have any sort of angular momentum, L1, L2, and L3. If we combine L1 and L2, we get some sum, let's call it L prime, that lies between the maximum and minimum possible values. We add to that L3, we can get all kinds of possible total angular momenta. Let's consider a special case where we want the atom to have an overall total angular momentum of 0. If we add the L prime to the L3 to get 0, this is possible only if we take L prime to be exactly L3. Thus, the condition that our atom has total angular momentum equal to 0 is the triangular inequality relating the 3 angular momenta. Now, the parity of an orbital with angular momentum L is just -1 to the L. So the parity of the 3 electron state is simply -1 to the power L1 plus L2 plus L3. Now, I want to explain briefly the technique that Slepian and Eisenstein developed for measuring efficiently endpoint correlations. What we do is we imagine the density around some point at the origin, and we divide it up into shells that have some radial bin, and then we project out the components according to the various spherical harmonics. And from those, we can reconstruct the total distribution of density, albeit in bin values of R, in terms of these coefficients, A sub Lm. We can sort of think of this naively as a bunch of orbitals, electrons running around a very primitive atom, where we have here 3 different orbitals corresponding to 3 different bins in R. And this is a bit like what quantum mechanics was in the early days before the Schrödinger equation, and people imagined that the electrons ran in these orbits. In fact, I have a picture here from a famous text written in 1923 that shows how the radium atom was envisioned at the time. I think it's rather beautiful and amusing. Now, let's go back to the situation where we've developed an atom whose total angular momentum is 0. If the orbital angular momenta are 1, 2, and 3, for L1, 2, and 3, we can see that the sum is even, and that's a parity even state, and similarly for 1, 2, 1. But if we had, say, 3, 4, 4, that would be parity odd. In each case, we, of course, have to make sure that you can actually combine those angular momenta to make a total of 0. Now, 4-point correlations are like 3 electron atoms. So if you sit on one of the 4 galaxies and look at the distribution of matter around that galaxy, or the distribution of galaxies really around that galaxy, the 4-point correlation function is given by the expectation value that's shown here. I mean, delta here is the deviation of the density from the mean density. And this is the standard correlation that one would want to measure as a 4-point correlation. Now, if we assume homogeneity, of course, this expectation value can't depend upon the absolute location, and we can translate each of those vectors by a fixed amount. And in fact, we can fix it so that the first one has argument 0, and then there are some other locations for the other 3 points. And if we consider this expectation value and now impose isotropy as a basic cosmological principle, we know that this function, which I've just called here f of these of R1, 2, and 3, would have to be isotropic. So this takes us to the question of isotropy and how to best express that in these calculations. By isotropy, of course, I simply mean that if we rotate all three of the vectors by the same amount, the function is unchanged. And of course, the way we are going to construct such functions is to use combinations of spherical harmonics. And so here I've written spherical harmonics as functions of the angles of 1, 2, and 3. And then there's some combination of these which will turn out to be isotropic. And how do we find that? Well, the standard way to do this is just to combine the angular momenta with Clebsch-Gordan coefficients. And a particularly symmetric and beautiful way of doing that is to use not exactly Clebsch-Gordan coefficients, but to use something called the Wigner 3J symbols. And I've written, I've displayed one of these here. And so if we weight the spherical harmonics, the three spherical harmonics, by this 3J symbol, the result is an isotropic function. That is, it has total angular momentum equal to 0. And it therefore follows that any isotropic function can be written as a sum of such functions where the lambdas take on all possible values, L1, L2, and L3. And then there are some coefficients which depend upon the actual magnitudes of R1, R2, and R3. In practice, we'll always use bind values for R1, R2, and R3, but you could write this as a very general proposition. Now, the way that the function z sub lambda is determined is it's just found by combining the measurements we made of those shells, the a sub LMs, together with these magic coefficients, which produce things that are isotropic. So once we've measured the A's for one single central galaxy that we've picked, we can calculate z sub lambda. And then we do this over and over again, taking different galaxies as the center points. And so this basically solves the problem of actually computing the 4-point function or the n-point function. And by this scheme that Eisenstein and Slepian developed, this is actually something that can be done very efficiently on the computer, whereas if we really tried to calculate all the quadrilaterals, all the tetrahedra, it would be completely hopeless. But this cuts through that problem. Now I want to go off on a slight tangent just for a couple of minutes. There's something called the Gaunt integral, and I've written here the Gaunt integral, which is the integral of three spherical harmonics. And it's possible to show that it can be written in terms of those Wigner 3J symbols in the following very symmetric way. You can see that you can see the symmetry between the L's and the M's is displayed in this result. Let me mention that when Gaunt did this, why is this called the Gaunt integral if it's so simple? When Gaunt did the integral originally in the 1870s, there were no Clebsch-Gordan coefficients or Wigner 3J symbols. He effectively calculated the values of those 3J symbols, which is a very non-trivial calculation. So that's why Mr. Gaunt's name is in fact attached to this result. It turns out that what we need is something analogous to the Gaunt integral. Instead of having three spherical harmonics, we have three of our isotropic functions, which are each one of these is a function of three unit vectors, R1, R2, and R3. I've simplified the notation here just by writing a capital R hat, but that stands for the three unit vectors in the directions of R1, R2, and R3. And so we multiply together three of these, just the way we multiply together three spherical harmonics, and then you integrate over all the angles. That dr hat stands for integrating over all three angles. And that's written maybe more explicitly here. And so that's something you have to compute. And we did it. And here's the result that you find. And that funny thing in brackets here with 9 values in it is called the 9J symbol. And this is the result of that calculation. And the lambdas, we have 3 different lambdas, and each lambda has 3 components. So altogether, we have 9 pieces. They fit in here very nicely and very symmetrically. Now comes the hard part of the game. Measuring the various components of the 4-point correlation isn't so hard. What is hard is calculating the covariance between those measurements. Now, if we just ask for the general covariance between the 4-point function, you can write it in terms of this integral. So you see here we have a factor, which is the 4-point function, and then we have the 4-point function offset by some distance s, and then at some different locations, not r0 prime, r1 prime, r2 prime, and r3 prime. And the idea here is that we want to know what is the covariance between the measurements of the correlation at one location of values of r and values at r prime. And this can be computed formally in the way that I've written down. Now, how can we make any progress? This is hopelessly complicated. The way we make progress is we assume that the delta, the fluctuation in the density is a Gaussian random field. And what's a Gaussian random field? A Gaussian random field is a field where every expectation value is simply the result of 2-point expectation values. There are no higher correlations than 2-point. And if you want to know what's the 4-point correlation, well, it's just a product of 2-point correlations. And so our expectation value of 8 deltas then must be made up of 4 expectation values of pairs of deltas. And we were able to do this calculation now because the expectation value of delta of R1 and delta of R2 is, of course, the 2-point correlation function, which is something that's measured and known. So that means that by assuming that for the purposes of the covariance, we can assume a Gaussian random field, it must be that we can actually calculate it. Now, the question is, how do you do that? Well, the pieces that come into the calculation necessarily involve that 2-point correlation function, or sometimes more practically, the Fourier transform of that, which is, of course, the power spectrum. And it turns out then that the fundamental quantities that we need are some integrals that we call f of R1, R2, and R3, and that's labeled by 3 values of L. And you see that all it is the integral over the 3 momentum magnitude of the power spectrum multiplied by 3 spherical Bessel functions, where the R1, R2, and R3 all appear. So this is one fundamental quantity. And since we know the power spectrum, we know these Fs for all values of L. I mean, they have to calculate it, but there's something that we know. And the other important ingredient is this quantity that we call the generalized Gaunt integral that connects that is the integral of 3 of our isotropic functions multiplied together. And that's a result I already showed you. You put all this together, you get an answer, which is in the paper that John Min is the first author of. And there are a few quantities in here that I haven't explained, but they're all fairly simple. The D's and the C's are the 2 things that I haven't really explained. But otherwise, you can see the F functions, and C here is, of course, just the 2-point correlation, and we have the 9J symbol. So it's kind of a messy expression, but the fact is that we know all the pieces in it. And actually, this is only 1/2 of the answer. There's another piece. that looks very similar. But the point is that we can actually calculate analytically the covariance matrix under the single assumption that we can use a random field approximation. Now, in practice, this isn't the only thing we need, because we've made the assumption of Gaussian random field, which isn't perfect, but we can use this analytic covariance matrix as a template, and we use it together with a large number of mocks to make the best covariance matrix that we can. As you can see, this is still a bit of an art. We're still dependent on having high quality mocks to work with. And in my opinion, this still remains as the biggest challenge in looking for cosmic parity violation in large scale structure, because if we make an error in the covariance matrix, that's essentially just saying that we get sigma wrong. And if we underestimate sigma, we may see fluctuations that look bigger than they should be, and would be evidence then signals that would be bigger than the fluctuations we expect, and would indicate parity violation. So we have to make sure we get the covariance matrix correct, so that we don't find an effect that may not be there. All right, I hope that this gives you at least a brief introduction to this subject without going into too many details. Here are references that I think cover all the material that I talked about today. Thanks.